Hello viewers and subscribers of this channel. In this video we will derive several formulas that are very important for control system design. We will explain and derive the equation that relates the peak time with natural undamped frequency and the damping ratio. Here's the formula. Then we will derive the formula for overshoot. Here's the formula. We will show that the overshoot only depends on the damping ratio. Then from this formula we can easily derive the formula for the percentage overshoot that's given over here. And finally, from this formula we can basically express the damping ratio and show that the damping ratio is only a function of the percentage overshoot. The importance of the formulas derived in this video can be best illustrated by the following example. Now, imagine that you are a control system designer and that you want to design a PID controller that will stabilize your system and that will achieve a certain desired closed-loop system transient response. Basically, let us say that you're given a task to design a feedback controller that will achieve the following transient response specification. Your overshoot, expressed in percentages, should be smaller or equal than 20%. So let us illustrate this design specification graphically. This is our time axis, and this is our response, y of t. Your step response, in ideal case, should look like this. So, what is now the percentage overshoot? The percentage overshoot is basically this value over here, MP, represented with respect to percentage of your steady state value, YSS. So MP percentage is MP divided by YSS multiplied by 100%. Our closed-loop system should behave like this. On the basis of this specification, we have to tune our PID control algorithm. One of the ways for tuning the PID control algorithm is to determine the closed-loop pulse of the system. And one of the important parameters of the closed-loop pulse is the damping ratio. Now, I will give you a formula and I will derive you that formula in this video that will give you zeta, or your damping ratio, as a function of MP percentage. Furthermore, I will derive you a formula that will relate the peak time with damping ratio, zeta, and natural undamped frequency, Wn. So, these two parameters are very important because they determine the locations of the closed-loop poles of your system. So, given the specifications on Tp, for example, we can find zeta and omega n. We can basically find the locations of our closed-loop poles, and from there we can go backwards and we can design our PID controller. Before I start, I would like to mention the following. First of all, I created a post that nicely summarizes everything that I will explain in this video. Here you can see the post. This post contains graphs, contains all the equations, and contains all important derivations. Then, It took me a significant amount of time and energy to create this post and this video. Consequently, I kindly ask you to subscribe and press the like button. Thank you very much. Okay, so let's start. First, we will derive the formula for the peak time. We start from the prototype second-order system that's given by the equation number 5. Basically, this is a general form of the transfer function of a second-order system. Here, S is the complex variable, omega n is the natural undamped frequency, and zeta is the damping ratio. Basically, zeta and omega n have a nice graphical interpretation that's shown in this figure over here. Basically, omega n is the distance from the origin in the complex plane to the pole of the transfer function. Zeta is basically equal to the cosinus of the angle between this vector over here and the real axis. Then, if we multiply zeta and omega n, we get the real parts of our pole. And if we multiply omega n by square root of 1 minus zeta squared, we basically get the imaginary part of our pole, and this imaginary part is called basically the damped frequency. When deriving the formulas, we assume that the input of the system is a step signal. So let us illustrate this situation graphically. Here's our system represented by the transfer function. Here's our input, and the input is basically a step function. This is time, this is u of t. And the output of the system for such a step input signal looks somehow like this. This is time, this is y of t. In the Laplace domain, the step response can be represented by the equation number 6. The whole idea of deriving the peak time and the overshoot is to find the analytical expression for the step response in the time domain. And this analytical function describing the step response of the system in the time domain is given by the equation number 7. To make this video as short as possible, I will not derive the equation number 7. However, if you want to know how this equation is derived, you can click over here, and this link will lead you to another lecture and another video I created that explains in details how to derive the formula, the analytical formula for the step response. This video contains all the derivations and all the equations and graphs. Okay, so let us go back to our formula. What is interesting over here to observe? First of all, this is a damped function. Graphically, this function will look like this. This term over here is basically an envelope of the oscillations. And this sinusoidal or harmonic term over here will describe these oscillations. The whole idea of deriving the peak time and the percentage overshoot is to find time for which this function achieves the maximum value. Okay, so how to find the maximum value? Well, we need to compute the first derivative of this function with respect to time. And once we have the first derivative, we need to set the first derivative to 0. And this equation over here will give us the candidates for the maximum or the minimum of the function. Now, let us try to find the first derivative. Before we try to even find the first derivative, we need to basically introduce this notation. Zeta times omega n will be called alpha, and omega n multiplying the square root of 1 minus zeta squared will be called omega. Again, alpha and omega have a nice graphical representation that can be seen on this graph over here. Okay, by using this new notation, we can express our original step response by the equation number 9. Next, let us expand the equation number 9. We will expand the equation number 9 by using this trigonometric formula over here that you have probably learned in basic calculus. By using the equation number 10 in equation number 9, we obtain the equation number 11. Now, let us simplify the equation number 11. First of all, let us simplify this term over here. Cosinus of inverse cosinus of zeta is actually equal to zeta. Then, let us simplify the term over here. We basically need to compute the sinus of inverse cosinus of zeta. And in order to simplify this term, we need to go back and look into our graph that you can see over here. Now, inverse cosinus of zeta is actually equal to theta. So we need to compute the sinus of theta. The sinus of theta from this graph is equal to omega over omega n. Furthermore, omega is equal to omega n multiplying square root of 1 minus zeta squared. And if we divide that by omega, we will simply obtain square root of 1 minus zeta squared. So that's our simplification for this term. By substituting the equations number 12 and the equation number 13 in the equation number 11, we first obtain this equation over here. Now, let us further simplify this equation. The term over here can go inside of the brackets, and we will obtain zeta divided by square root of 1 minus zeta squared, and the term over here and the term over here cancel, so we obtain here 1. Okay, that's good. Let us simplify this expression further. If we multiply the denominator, the numerator, better to say, over here by omega n and the denominator by omega n, we obtain this term over here. The term in the numerator is our alpha, and the term in the denominator is our omega. And the last equation in the equation number 14 is our final expression for the system response. Now, we need to compute the first derivative of this equation. This equation can be represented as follows. We can write y is equal to 1 minus f of t multiplying g of t, where f of t is equal to e to the power minus alpha t, and g of t is equal to alpha over omega sinus omega t plus cosinus of omega t. Now, let us see what is the first derivative of y. Basically, the first derivative of y with respect to time is 0, since this term is equal to 0, right? Minus f prime of t multiplying g of t minus f of t multiplying g prime of t. Here we have used the product rule for derivatives, and by using these steps and by applying these steps to our function, we can obtain the final expression for the first derivative of y. Let us analyze this expression over here. Y dot of time is a product of two functions. The first function is e to the power minus alpha t. The second function is sinus omega t, and the third term is actually a constant, and this constant is equal to alpha squared over omega plus omega. Let us now discuss the terms under which this function is equal to 0. E to the power minus alpha t cannot be equal to 0 for finite values of time. This is not possible. Constant cannot be equal to 0, so we have that sinus omega t should be equal to 0. To repeat, first derivative is equal to 0 if and only if sinus of omega t is equal to 0. Now, how many solutions this equation has? This equation actually has an infinite number of solutions, and these solutions are given by basically omega t is equal to k multiplying pi, where k can be 0, 1, 2, 3, etc. So our first candidate is obtained for k is equal to 0. If k is equal to 0, t is equal to 0, and this is the beginning of our transient response. Consequently, this cannot be the maximum. The second candidate is obtained for k is equal to 1. For k is equal to 1, we obtain omega times Tp is equal to pi. And from this equation, we can obtain that Tp is equal to p over omega. And this will be our maximum over here. So going back and substituting the value for omega in this equation, and omega is equal to omega n multiplying the square root of 1 minus zeta squared, we've obtained the final expression for Tp. Basically, the maximum or the peak of the function can be found by substituting the Tp in our starting equation. And our starting equation is given over here. By performing this substitution, we can obtain this equation over here. This equation comes from the fact that sinus of omega Tp is equal to 0. Now, this equation can be further simplified and can be represented by this equation over here, and if we use the expressions for Tp and alpha in this equation, and if we cancel omega n terms, we obtain our final equation that's given over here. However, we still need to compute the peak value. The peak value is usually denoted by MP, and it is defined by this expression, by the equation number 19. So we take the peak value of the function and we subtract from this peak value the steady state value of the function. Now, the steady state value of the function is equal to 1, and this follows from the finite value theorem since the system is stable. Basically, if the control system is well designed, then our steady state value will approach 1 in the step response. That is, the steady state error will be equal to 0. By performing this substitution, we obtain the overshoot value. So the overshoot value is an exponential function. The percentage overshoot, denoted like this, is defined by taking MP and dividing the MP by YSS and multiplying the result by 100%. Since YSS is equal to 1, we basically obtain the percentage overshoot, and the result is given by the equation number 23. And finally, let us derive the formula that gives zeta as a function of percentage overshoot. Basically, we need to invert this equation. From the equation 23, we obtain this first equation. Then, if we take natural logarithms of both sides, e and natural logarithm cancel, so we obtain this equation over here. Next, we take a square of both sides, we obtain the equation over here. After some transformations given by this equation and this equation, we can basically obtain zeta square, the formula for zeta square. And going further, we can obtain zeta by taking the square root of this fraction. Here you should be very careful while taking the square root, since square root of x squared, where x is a real number, is actually equal to absolute x. And here you should be very careful because the square root is a positive function. By using this rule, we obtain this equation over here, and now here we can basically see that ln of this term over here is a negative function, so consequently we will take a negative sign over here to get rid of the absolute value. And here is our final expression that gives us zeta as a function of the percentage overshoot. Okay, so let us now numerically investigate the accuracy of these formulas. So what do we do over here? We define a prototype second order system with zeta equal to 0.4 and with omega n equal to 2. Then in MATLAB we define the transfer function and we compute the step response of the transfer function, and the step response is given by this graph over here. In this graph over here we can approximately find the peak time, that's denoted by x, and the maximum value that's given by the value of y. So we obtain from the graph that TP is 1.25 and MP, here is an error, is not equal to 1.73, is actually equal to 0.253. I will correct this later. That is, I will correct the post later. So let us now try to verify that our formulas for TP and MP are correct. So substituting the values for zeta and omega n in the equation number 1, in this equation, we can compute the TP value. And as the result, we obtain the TP value of 1.71. Next, we will use the equation number 2 to compute the overshoot. So by using this equation and by substituting the value for zeta, we obtain basically the value of 0.2538. Now, comparing these two values, 1.71 and 0.2538, with the values that we see over here, we can actually conclude that the formulas, that is the analytical formulas that we have derived in this video, are able to accurately predict the peak time and the maximum value of our step response. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please subscribe and support my channel. Thank you very much and have a nice day.